Thank you very much.
Now you have to delete that thing.
Yeah. So, well, actually, part of this work was initiated during the first part of the TRR. So I'm very happy to come back here and update you about what happened afterwards. And as you can see, the title of my presentation is Extremely Weak Meridional Transport and Hemispheric Heatwaves in Northern Hemisphere Mid-latitudes, which is where I will be leading you after an introduction of the work that I have been carrying on for 4 years, well, 5 years now, actually. I want to give credits to the people that have helped me in this endeavor. Most recently, my colleagues at CNR-ISAC, Susanna Corti and Federico Fabiano, but also Davide Faranda and Flavio Pons from IPSL in Paris. There Melinda Galfi, who was also a colleague in TRR and now is in assisting professor in the Vrije Universiteit Amsterdam. Rune Gravesen from Tromsø. Valerio Lucarini, currently at Leicester University and also PI to the phase 1 of TRR. And Gabriele Messori from Uppsala University. So I want to start really from the, well, let me first give you an outline of what I will be discussing about. So first of all, I will try to convincing you about the sporadic and intermittent nature of the meridional transport in the Northern Hemisphere mid-latitudes. And then I will show you how we manage to decompose zonally the meridional transports in order to analyze the contribution by the different scales of the dynamics in the atmosphere. And then I will give you a remarkable example of an extreme meridional transport in hemispheric scale, which was the June-July 2021 Northwestern Pacific heat wave that you might have heard about. And then I will try to generalize what I will be discussing with that case study to convince you that this extreme event was typical in its own way. So as I said, let's start with the real basics. So where is this meridional transport coming from? Well, it comes from, of course, the latitudinal imbalance of energy input at the top of the atmosphere. These are just meridional sections of the energy budgets that were computed by linearly combining radiative and heat fluxes. So the green one is the top of atmosphere energy budget. That you can see that is, of course, positive in the lower latitudes and negative in the higher latitudes. The red one is the energy budget in the atmosphere that basically sets the case for the zonal mean general circulation, and you see that there is a relative minimum in the around the equator because of the ITCZ, and the surface or oceanic heat budget, which is the brown curve. If you just integrate this zonally, you will end up with something like this, in which you see that, okay, by convention, the sign of the transport is positive if poleward, if northward, you will see that you have a very smooth total energy transport, which is, of course, positive in the northern hemisphere and negative in the southern hemisphere. And you will see that this energy, total energy transport is somehow partitioned into an atmospheric and oceanic component, the red one being the atmospheric and the brown one the oceanic. You will see that also the atmospheric heat transport is relatively non-symmetric around the equator because it's negative at latitude 0, because the ITCZ in the annual mean is, of course, currently situated in the northern hemisphere tropics. So the interesting thing is that if we focus on the atmospheric transports, and if we focus on the atmospheric transports in the northern hemisphere mid-latitudes, we can see that the probabilistic distribution of these transports is non-Gaussian, and you can see it by combining the PDF of the V prime, which is the anomalous meridional velocity, and H prime, which is the anomalous energy. And you see that the quadratic term spans a few orders of magnitude between 0 and 20 petawatts, so to say, with a median somehow around 3-4 petawatt in the annual mean. So these transports are really non-Gaussian, and this has physical implication because the strongest meridional heat fluxes happen to be collocated in the northern hemisphere with the region of largest baroclinic activity, which means that not only the most of these meridional transport has to be associated with the mid-latitudinal atmospheric dynamics, but also that the role of eddies is more important in setting up this non-linearity than the role of the zonal mean circulation. You can see it also if you look at the time series. This is from Anbaum and Novak 2014, and you see this is an example of some sporadic extreme in the heat fluxes during DJF 1994-1995, where you see that the extremes of baroclinic activity in blue are collocated with the extremes of heat fluxes, and also that they are anticorrelated, so that when you have a maximum peak in the heat flux, you have a minimum in the baroclinic activity. This also has implication for a seasonal budget of energy across the mid-latitudes of the northern hemisphere. We see here examples of seasons between 1993 and 2005, and if you count how much energy is carried through transport in the top 99 percentile of the distribution throughout the season, you will see that in some season the amount of energy that is carried through these extreme transports can make up to 47, 55, 46% of the total energy that is carried throughout the mid-latitudes within a wintry season. So with this, I was trying to convince you that there is reason to look into the extremes of meridional heat transport. So what do we do? Actually, it is very simple. We take the total energy, which is the sum of the moist static energy with these first two terms, I guess you know this equation, are the dry static energy term, so the adiabatic and gravitational potential energy term. The moist term that accounts for the conversion of energy throughout phases, and the kinetic energy term, and we compute this product of the energy times the meridional velocity, and we integrate it vertically and also across the latitudinal circle. And this provides the amount of meridional transports throughout a specific phi, in this case, latitude. The new thing is that we do it wave number by wave number. So what we do is taking the Fourier coefficients A and B for a psi, with psi being the meridional velocity and the total energy, and we combine them like this in order to obtain the amount of meridional transports that is carried by the specific zonal wave number n. This is what looks like in the annual mean. So the total energy is the solid black curve. Okay, this is inverted compared to before. So we now have the northern hemisphere to the left and the southern hemisphere to the right. And you see that if you only take the zonal mean term, which is wave 0, and we focus on the northern hemisphere mid-latitudes, which is this red rectangle here, so between 30 and 60 north. The zonal mean term is slightly negative in this region, but then if you sum up the wave numbers from 1 to 5, you end up with a positive term that is relatively homogeneous throughout the mid-latitudinal channel. And then if you also add the wave numbers from 6 to 10, you will see that you will find the annual mean peak of the meridional transport, which is in the northern hemisphere located somewhere between 40 and 45, let's say. So basically, by looking at this in the annual mean, what do we get? We get that half of the energy is carried by the what we will refer to as planetary scale waves, so waves from 1 to 5, and half of the energy is carried by the waves from 6 to 10, and that the meridional distribution of the planetary scale is relatively homogeneous, whereas the meridional distribution of the synoptic scale has a gradient and peaks in the region between 40 and 45. So what we do now is using a probabilistic approach. So instead of looking at the median annual mean meridional transport, we look at the distribution of the daily meridional transport in DJF and JJA. So the green curves are the standardized PDS for the total transport, for the zonal mean term, so K0, for the planetary scale term, so wave from 1 to 5, and for the synoptic scale term, so from 6 to 10. And the blue and red PDFs instead are the PDFs of the extremely weak, or if you want, we refer to them as equatorward meridional transport, and extremely strong, or if you want, poleward meridional transport, respectively in blue and red. And we do it from DJF and for JJA. And what we see, first of all, is that, I forgot to mention that the extremes in the transport were computed on the total transport, so summing up all the wave numbers. This means that if we look at the zonal mean term, there is no spread in the standardized PDS between the poleward, equatorward, and extremes and all the transport. That means that the zonal mean transport doesn't contribute to the extreme transport, whereas the planetary scale and synoptic scale have different medians of the contribution to the extreme. That means that they are making up actually these extreme transports. We also see that there is quite a lot of seasonal variability in the planetary scales, as you see from the range of the total PDF. Whereas the seasonal variability of synoptic scale is less pronounced. Another interesting thing is that the eddy PDFs are far from being ocean. They clearly have a thicker tail toward the poleward transport than toward the equatorward transport. And this is even more pronounced if we look at the synoptic scale, as you know that the barochneic eddies are far from being linearly distributed. We do something more. We do the scatter plots of the planetary scale and synoptic scale transports in the 2 seasons. And basically, this confirms once again that there is a more pronounced planetary scale seasonality than synoptic scale. And also, it shows quite clearly that there is a linear relation between the extreme in the synoptic scale and extreme in the planetary scale. That means that basically within the extreme transport, either you have an extremely strong planetary scale transport or you have an extremely strong synoptic scale transport, but not both. So for now, what we did is considering all latitudes within the 30 to 60 latitudinal channel as being equally probable. So we basically compute the PDFs out of all the extremes that were happening somewhere in this latitudinal channel. The next step that we did was considering the latitudinal distribution of these PDFs. So what I'm showing here is basically, you can think of it as a projection over latitudes of the PDFs that were so far just 1D. So for each of the latitudes, you have the shadows that resemble denote the PDFs of the total transport, and the red and green dash solid lines, dash dotted lines, denoting respectively the planetary scale extreme PDF and the poleward extreme transport and equatorward extreme transport. So this is for the total, and this is just the zonal mean, and this is the planetary scale, this is the synoptic scale, and this is the higher order scales. So what we see interestingly here, this is for DJF, okay? What is interesting here is that once again, the median zonal mean transport across this circle of latitudes is relatively weak. It ranges between 1 and minus 1.5, and that most of the transport is carried through the planetary scales that peaks around 52.5 at almost 5 petawatt, and by the synoptic scales that peak at 3 petawatts and around 37.5 north. Another interesting thing is that if you look at the PDFs of the extreme transports, these are very much diverse from each other at every latitude for the planetary scale. That means that basically no matter what is the median value of the planetary scale, the planetary scales are still contributing to the extremely weak or extremely strong transport at every latitude. Whereas if you look at the synoptic scale, you will see that they are contributing to the extreme only if the median synoptic transport is strong. That means that whenever at the latitudes where the synoptic scale eddies are vanishing, these are not obviously contributing to the transport. Let's have a look at the JF. Of course, in the total, the transport is much weaker. The PDF is much more sparse in the central part of the circle of latitude, whereas it is more concentrated. It has a smaller standard deviation in the lower corner and upper corner of the circle of latitudes. Once again, the median planetary scale and synoptic scale contributions are opposed. So whenever there is the median peak of the planetary scale, you have a weak synoptic scale and vice versa. And again, the PDFs of the extreme transports denote that the planetary scale are contributing to the transport everywhere, whereas the synoptic scale are contributing only whenever the median synoptic scale transport is strong. This is just once again, a confirmation of why these PDFs are non-normal. This is the skewness of the distributions as a function of latitude for the total and for the extremes. And the dashed lines are summer and the solid lines are winter. And you see that already the median, the overall distribution is positive everywhere, ranging between 0.1 and 0.4. And if you look at the PDFs, the skewness of the PDFs in the extremes, these are the equatorward, and they are always negative. But of course, you have to reverse it because basically all the transports are negative there. So in absolute values, it ranges around 1.3. And regarding forward transport it ranges between 2.2 and 1.3, depending on whether you're looking at summer or winter, with a tendency for highest unities in the lower latitudes for forward transports, and in the higher latitudes for equatorward transports. So let's go a bit more into the dynamics of the atmosphere. What we do now is computing for every day in the reanalysis period the closest weather regimes in different domains of interest. So in the Eastern Atlantic and Europe, in the Pacific region, and in the whole of the North Atlantic circle of latitude. And then what we do is looking at how if a specific weather regime is made more frequent or less frequent by the occurrence of a meridional transport extreme. And what we see by looking, for instance, at the poleward extremes in DJF is that whenever there is an extremely strong meridional transport, you will have an increased frequency in the NAO minus regime. That means that basically you have enhanced zonal circulation in the central lower part of Europe, whereas the NAO plus regime, that is, I mean, basically the Iceland semi-permanent law is becoming less frequent. And regarding the Pacific domain, the Pacific trough regime that basically features a semi-permanent low over Alaska and the ridge over central North America is made more frequent. And regarding the Northern Hemisphere is kind of confirm what we looked at in the regional domains, because the AO plus AO minus regime is becoming more frequent. That looks pretty much similar to the NAO minus, and the Aleutian ridge regime is becoming less frequent. The pattern is reversed quite symmetrically if instead of looking at poleward extremes, you look at equatorward extremes. Yeah, okay. Let's have a look at summer. So there are no nice names for the summer weather regimes. So I denoted them as EATC1, EATC2, EATC3, and EATC4, and so forth for the different domains. And what happens with the poleward extremes is that the EATC2 pattern, which looks a bit like something in between a Scandinavian blocking and Atlantic ridge pattern, is becoming more frequent, whereas the EATC4 is becoming less frequent, which is basically the symmetric counterpart of the EATC2. That means that you will have less frequent occurrence of Atlantic low pressure systems during summer for extremely strong transports. And for Pacific, you will have a decrease in the frequency of this kind of pattern, which looks a bit like the PNA, the Pacific trough weather regime that we already saw in winter. And for the overall Northern Hemisphere circle of latitude, you will see that the NHC4 pattern, that is very similar to EATC2, actually becomes more frequent when you have poleward extremes in the transport. And again, you have to reverse the pattern if you look at the equatorward extremes in the transport. Okay, so let's come to the case study. I think that, yeah, all of you have heard of this extreme Northwestern Pacific heat wave in 2021. They reached temperature up to 47 degrees Celsius in the immediate inland of the Canadian Pacific coastline. There were lots of fires. There were very relevant damages in crops, and a lot of people have studied this occurrence. And there was also a preliminary report by the World Weather Attribution that was trying to argue how more frequent this kind of event was made by the anthropogenic climate change, saying that this event would have been virtually impossible, using their words, without the anthropogenic climate change. There were studies about the unprecedented nature of this heat wave compared to paleoclimatic proxies. In this case, by Hitler et al. 2023, they used proxies of the last 2 millennia, I think from, I don't know if this was paleotrans or something else, and they were finding nothing like this in the last 2,000 years for this kind of events. Also comparing this event with other kind of remarkable heat waves in the world across the last 20 years, it was found that this event, although being much shorter than other heat waves that were taken into consideration, were exceeding much more standard deviation of the distribution of the maximum 2-meter temperature compared to the July-August 2003 heat wave in Europe or the July-August 2010 heat wave in Russia. That was really, remarkable event. White et al. 2023 in this paper also tried to explain what was the synoptic situation that was leading to the unfolding of this heat wave, and they found that there was an advection of cold and moist air from eastern Siberia into the central Pacific that was leading to the development of a very strong low pressure system, and finding a pre-existing pattern of warm SST anomalies. This low pressure system, by building up the warm front on the western side of it, was bringing a lot of diabatically heated air into the Northwestern Pacific coast of North America. And so, the question is, was this kind of development exceptional, and could it be related to some sort of extreme heat transport? So the first thing that we tried to do was, since we are considering zonally average meridional heat transport, can we zoom out from the Northwestern Pacific and consider the whole of the Northern Hemisphere and see what if the event from a temperature point of view could be considered as an hemispheric event. So we performed composite mean maps of these of land surface temperature, of sea level pressure, of SST, of wind speed at 250 hectopascal, and of total precipitation in the period between the 24th of June 2021 and the 5th of July 2021, to show that there was not only an unprecedented heat wave happening in the Northwestern Pacific coast of North America, but there were also strong anomalies in eastern Siberia and also in wide part of Central Asia and European Russia. Actually, if you have the LST hemispherically over those days, you will also find that the anomaly for this quantity lies in above the 97.5 percentile of the climatology of hemispheric LSTs. From a synoptic point of view, not surprisingly, we find that there is a ridge off the coast of southern Alaska, where those basically providing energy for the building up, energy, the synoptic condition for the movement of the warm front from the central Pacific. There were strong cold anomalies in the center, SST anomalies in the center of the Pacific, and strong warm anomalies west of it. So that means, and this was because basically this was related to the fact that the low pressure system found energy to deepen into this part of the ocean, and then to find energy to fuel up this warm front toward the coast to the west of it. The wind speed at 250 hectopascal, which is a measure of the jet stream, signals that the jet stream was very much displaced very north into the Arctic Canada, and also this band of precipitation off the coast of Siberia into the Central Pacific basically is tracking the advection of cold air that was fueling the development of the low pressure system. Okay, so this is nothing new, basically. It's just confirming what White et al. In 2023 were already discussing. But let's have a look at the meridional transports now. So this is the Moller plot of the meridional transport throughout the summer season of 2021. This is zonally average, and this is as a function of latitude. I put the dashed vertical line at the start of the heat wave, so on the 24th of July 2021, and you see that this occurs basically consistently with the development of a very weak meridional transport anomaly, especially in the upper half of the mid-latitudinal channel. And actually, the day that I highlighted with this vertical dashed line was also a day of exceptionally weak meridional transport in the zonal average. That means that it was not only a local event, but as it was suggested by the by the temperature patterns, it was an hemispheric event. So let's have a look at the spectrum of this meridional transport. So this is the energy divided by wave numbers as a function of latitude. This is the anomaly of the spectrum, and this is the climatological spectrum for JJA. So if you look at the climatological spectrum, you will see that there is basically a dispersion relation, if you want, in the wave numbers from 4 to 8. So you start from the higher latitudes toward the lower latitudes, and there is a peak in the lower latitudes for K3. If you look at the anomalies, you will see that there are very strong this is for the period between 24/6 and 5/7/2021. So in the occurrence of the heat wave. So if you look at these anomalies, you will see that they are very strong, up to -1 watt per meter per kilogram anomalies of transport in the middle of the channel for the K3, and also in the upper part of the channel for the K4, and also for K6 you have negative anomalies, although they are a bit weaker, and also for K8 you have negative anomalies. So the interesting thing is that if you sum up all these, but especially the contribution by K3 and K4, you will end up with a transport that is actually becoming negative. So instead of going poleward, the total transport happens to go equatorward in this period. And I chose to look the Moller plots of the K3 contribution. Again, the dashed line is the start of the heat wave, and you see that in the occurrence of the unfolding of the heat wave in the upper half of the mid-latitudinal channel, you have a negative K3 transport up to -2.5 watt per meter per kilogram. And this is probably responsible for the extremely weak and actually slightly negative, as I mentioned, total transport during this period. Okay, I'm showing here other examples of heat waves that were associated with extremely weak meridional transports. This is for the second half of July 1998. Sorry, this is 3, it's not 2, there's a mistake here. This is late June 2006. This is early June 2016. This is early June 2011. In all these cases, you see that the K3 contribution becomes negative and provides basically a vanishing or extremely weak total meridional transport. So I brought all these cases together of hemispheric heat wave and extremely weak meridional transport. I found roughly 34 cases out of 190 cases of hemispheric heat waves in the 1979-2023 period. And I performed a composite mean of some fields throughout these cases. So this is the sea level pressure, this is the SST, this is the LST, and these are the areas where I have an exceedance of the 0.25 occurrence of heatwave events in the domain of these combined or compound extreme events. So what we see, anyhow, what is important and what I want to show here is that in all these cases, you will have a significant warm anomaly over the western coast of North America, and also over much part of Eastern Europe, which is consistent with what happened in the 2021. You have tendency towards negative anomalies of SST in the center of the Pacific, although you will see that this is not significant, whereas it is significant that you have positive SST anomalies in the Northern Atlantic in the occurrence of these compound events. And most importantly, you have a ridge of sea level pressure over the western side of the Northern America, which is consistent with what we found in 2021, and also you have positive anomalies ridges over the Western Siberia. So how do you explain this? It is not easy actually to find a common pattern in it, but our understanding is that the phase of the K3 contribution is somehow modulated by the lengthy contrast, so that since the heat wave is happening simultaneously over all the continents, it is basically providing an excessive lengthy contrast that is basically favoring the buildup of the ridges over the western side of the continents and our troughs within the oceans. And this is particularly evident in the Pacific region, whereas it is a bit more difficult to understand. At least we have more contrasting results regarding the Northern Atlantic. The interesting thing is that you can do the same with DJF in winter. So these are the composite mean maps of extremely, so hemispheric LST anomalies in winter with extremely weak meridional transport occurrences. And you will see that here it's even easier to understand, because if you look at the sea level pressure, you will see that you have a significant low anomaly over the Arctic, or if you want, over Western Siberia, that is extended into the continents, into the Eurasian continent, and you have ridges over both Pacific and the Atlantic, and you have very strong LST anomalies over the Central Siberia, over China and East Asia, and over the center of Northern America. Whereas the pattern of SST is a bit less clear. But anyhow, by already looking at this, it is easy to understand that when you have an extremely weak meridional transport, you basically suppress the exchange of energy between the tropics and the higher latitudes. And basically you do this by fueling an anomalously zonal circulation that is bringing warm, mild and wet air into the Eurasian continents in particular, and to some extent into the Northern America as well. We can also look at the spectra of all the composite events for DJF, and again you see that the anomalies, the negative anomaly is particularly strong in the K3 contribution, whereas the contribution by higher order waves is less relevant. So in this case, instead of reversing the sign of the transport, actually what the K3 contribution does, and you can see it by comparing these anomalies with the climatological DJF spectrum, it basically suppress the total transport by, again, fueling this extremely strong zonal circulation. Yeah, okay, so this is what it looks like for a specific season for 2006. Here is where you have an hemispheric heat wave, and this is the model plot throughout all of the season. You see that typically the K3 contribution is positive and is particularly strong in the upper half of the channel. but in the occurrence of these heat waves, or when the meridional transport is extremely weak, there is a reverse in the sign of the K3 contribution. Okay, I think I will skip this. One final thing I wanted to tell you is, okay, you might wonder why I did this kind of compound composite analysis. How much is this relevant? Well, actually, this turned out to be quite relevant because if you look at the relative frequency of hemispheric heat waves to the ratio, of hemispheric heat waves combined with the extremely weak meridional transport to the population of all hemispheric heat waves within a season, you will see that these hemispheric heat waves are in the 37.8% of the cases related to low meridional transport extremes, and in summer this happens in the 42.6% of the cases. So 1/3 up to almost 1/2 of the cases of hemispheric heat waves can be somehow associated with the occurrences of extremely weak meridional transport. And with this, I come to my conclusions. I provide a probabilistic approach to evidence the intermittent nature of meridional transports, particularly due to the planetary and synoptic scale eddies. I found that the planetary and synoptic scale eddies alternatively contribute to the extremely weak or strong meridional transports. And I found that the 2021 Northwestern Pacific heat wave is a typical occurrence of extremely weak meridional transports conditioned to hemispheric LST warm anomalies. And this could be considered as a compound extreme event. I also found that this kind of events is not isolated, and that the K3 contribution is key to understand the linkage between the regional pattern of the heat wave and the general circulation at the hemispheric level. And finally, I found that the sizable amount of hemispheric LST anomalies can be traced to, can be associated with the occurrence of extreme meridional transports. Okay, these are some references, and with